Welcome back. In this next section of the program, we will explain the procedures for time and frequency measurements using a variety of different waveforms. The oscilloscope is not only able to measure the amplitude of DC and AC voltage, but also the period or repetition rate of the voltage, as each division on the horizontal axis represents a known time interval, as defined by the time per division setting. A fixed DC voltage is one whose voltage and polarity remain unchanged within a given period of time, for example a battery, whereas the voltage produced by a signal generator is continually changing in amplitude and polarity many times per second. Using the scope, we can observe and measure these changes and determine the frequency at which they occur. Let's explain the measurement procedures. We'll begin with a square wave signal from the signal generator. To prepare the scope, switch the input coupling switch to ground and superimpose the trace on the horizontal center line using the vertical position control. Switch the input coupling switch to AC and adjust the volts per division control so that the waveform fills the screen. Set the time per division control to display 2 to 3 cycles. Check that the horizontal time-based calibration switch is set to the calibrate position. This will ensure that the reading taken from the time per division control is the correct value. Using the horizontal position control, position the leading edge of the square wave so that it is coincident with the left-hand side vertical graticule line. Count the number of divisions from here to the next leading edge of the square wave, that is to say, where the waveform begins to repeat itself again. Multiply the number of divisions by the setting on the time per division control. The calculation is 5 divisions times 0,2 milliseconds per division, which equals 1 millisecond. Therefore, the period of this square wave is 1 millisecond, which means that the time taken to complete one full cycle of the waveform is 1 millisecond. Having determined the period, we can calculate the frequency of this signal. The frequency of a waveform is defined as the number of full periods completed or traced out in 1 second and is measured in cycles per second or hertz. Frequency is expressed as the reciprocal of time, as the formula suggests. The time period to complete one full cycle is 1 millisecond. Therefore, the frequency is the reciprocal of 0,001, which equals 1 kilohertz. Let's look at another example, where the input signal is a sine wave. Set the scope to display 2 to 3 cycles of the waveform using the adjustment procedures described previously. Position the wave so that the positive going zero crossing point intersects with a suitable vertical graticule line. Once again, count the number of divisions from this point to the next positive going across point. The horizontal displacement represents the time taken for one complete cycle of the waveform to be traced out on the screen. Now apply the formula to calculate the frequency of the sine wave. 6 divisions times 0,1 millisecond per division equals a period of 0,6 milliseconds. Frequency equals the inverse of time, and so the frequency is 1 over 0,0006 cycles per second, or 1,666 hertz, or 1,666 kilohertz. Remember that time measurements can be made commencing at any convenient point on the waveform, as long as the time taken to complete one full cycle is accurately measured. Use the subdivisions on the center graticule line to assist in making an accurate measurement of time. When very high frequency signals are analyzed, the horizontal magnification switch is used to stretch the signal so that it is clearly visible on the screen. With these points in mind, let's calculate the frequency of this triangular waveform. The measurement of period is taken from any convenient point on the waveform to a point where the waveform repeats itself. Suitable measuring points exist between consecutive positive or negative peaks. To measure the period, adjust the horizontal time base to display 2 to 3 cycles. Adjust the horizontal position of the waveform so that a positive peak coincides with a convenient vertical graticule line. Adjust the vertical position of the wave so that the tips of the positive peaks touch the horizontal center line. The period is determined by counting the number of divisions and subdivisions between adjacent positive peaks. The number of divisions is 7,6. Now multiply the number of divisions by 10 microseconds, the setting on the time per division control. This gives a period of 76 microseconds, which is equivalent to a frequency of 13,15 kilohertz. Time for a break. After the break, we'll continue with other time-related measurements.